our next speaker, who wants to go with that mic? This is Mr. Mong-Kai Wu, student with the best
is your
DOT. And this talk was today about working on
start. So, hi everyone. My name is Mong-Kai Wu. One of the slaves in mutant fence group. And okay. So my topic is going to have a vertical cavity transistor laser. So here is my outline. I will give a bit of motivation and basic principle of the transistor laser, and we'll talk about the state of art edge-emitting transistor laser, and then I'll talk about my research like vertical cavity transistor laser and give the conclusions. So I think laser, 3-by laser is old topic, but why we're still working on it is just because we try to solve the problems that optical communication systems, because we have right now the data transmission is really, really high, and the copper interconnect apparently cannot match our need anymore. As you can see here, this chart, the x-axis is data rate, gigabits per second. The y-axis is energy efficiency. That means how many data you can transmit per joule. So this is kind of criterion we are looking at. So as you can see, a copper interconnect, it cannot surpass like a 30G. And this is just because you have like a skin effect when you try to modulate the high speed, you just get a very lossy. And so people try to use the diode laser, of course, for VCSEL right now is typical, like pretty good for a short distance communication system. But it also limited like below 50G because you have naturally slow recombination, about 1 nanosecond we'll talk about later. But if we try to expand this territory more, so we propose that transistor laser might be a good candidate for like data transmission, the optical transceiver for the next generation. So here is the typical VCSEL that is suitable for short distance communication applications, because the dimension is small and you have a lower external resistance and capacitance. And this device was made by UCSD, Larry Kogan, which is like state of art of VCSEL. It's like a 25 pair or something, and they will etch down, and you have oxidation confined the aperture over here. So basically, you can see the frequency response. This x-axis frequency, and you can see a 3 dB bandwidth is like 20G. It's pretty good, but this is diode laser, and what we call about what we talk about this some potential issue. The first is that slow carrier recombination lifetime. That's inherently limited by about 1 nanosecond. And second is that because usually for a laser, we also always have like a heterojunction between the P-type and N-type to confine the carrier. So it looks like the whole structure looks like a huge tank that stores lots of charge in the active region. So you can imagine it's hard to get rid of those charge once you try to modulate it. And further, you can see this is the diode. So the impedance is low, and when you try to operate a forward bias. So, but for the RF circuit, you have to consider the impedance match issue. So those low impedance will eventually limit your modulation speed. And those like slow carrier recombination and large minority storage charge time will eventually affect that you have a resonant band all over here. And this low resonant band will, of course, try to affect your eye diagram measurement. You will get overshoot on your eye diagram, and that will affect your bit error rate also. So why we said transistor laser probably will solve some problem over here, because you can see here is the band diagram of a diode laser, and this diode laser shows like a heterojunction N-type and P-type, but this heterojunction, of course, can give some benefits when you just dump over electron and hole into active region to further confine those electron and hole and recombine. But this is like a tank, like huge tank. You try to modulate it, you have to remove this carrier slowly, and that's why you eventually limit your modulation speed. But what is a transistor laser? Here we are talking about putting an extra quantum well in HBT base, in HBT structure. So here is like an emitter, and we put a quantum well in base, and here is a collector. So this HBT structure, the operation of HBT is pretty different. It's like we use a minority carrier transportation. So it's like a dynamic charge flowing into the base. So although we have lots of current coming in, but actually the storage of the carrier inside of the base is very low, because the carrier flow is mainly depend on the diffusion, the slope of here. So when electron coming in, they do a recombine. Those cannot be recombined fast. Will be swept out to the collector. So that's why we can achieve very fast transit time that we'll show you later. So here is our typical edge-emitting transistor laser. So you can see here, the top of it is the emitter. So we oxidize and leave the 1 micron of aperture over here. And here you can see this green and red color is a base with a quantum well. We put the base metal, and another side, the lower side is a collector metal, and we put the polyimide and do a VI in metal 1. So this case is like a 1 micron thick of metal, causing burning money. But that's why we got the high performance of a transistor laser. And you can see like a very interesting physics. Like basically, you can see this is family curve VCE versus like IC or optical power. You can see below this ratio is like a normal family curve, but above this ratio, because you switch from spontaneous emission to stimulated emission inside of this base region. So that means your recombination become faster, and so your beta will decrease, right? So, but it's just like this is electrical data, so you only need to see the electrical data. We know it's less because you change the recombination lifetime. And above that, you can see a different region. The king over here represents different recombination from ground state or first excited state. So that means for this transistor laser, you are not only like detecting the light output from this phase, but you also can extract the information from the collector side, I mean electrical signal. So this is the state of the art of our transistor laser. It's like, you can see this is edge emitting 400 micron device, and you have a 20 G bandwidth. Without and there's a resonance free, almost resonance free. And remember, this is 400 micron device, pretty large, as you compare conventional VCSEL. And you can see like this is the eye diagram we take. This is 40 gigabit per second, and you can show the optical simultaneous open of the optical eye and electrical eye. Yeah. So now the next question is, if we try to shrink down this device into like a vertical one, how fast it is, right? But it's not. It's pretty hard because before me. I mean, my mentor started this project already, and there's lots of issues we try to overcome, like cavity design, quantum well design, whatever. And this is a typical layout design we have in the first like 2 or 3 years ago. And basically, we try to copy the VCSEL, what VCSEL looks like put the emitter metal, base metal, collector metal, and do an oxidation and do a recombination. And this layout just totally fucked up, I can say that. It's just, I can tell you, you can see it from this family curve. Because you can see there's lots of offset voltage. That means your device is pretty resistive. And why it becomes resistive? Because you have to see this layout. You put the base metal, but you don't want to block a line. I mean, you try to confine a line into a small region because you don't want the light coming out and blocked by the emitter metal. But you remember this base region, the base thickness is pretty thin, couple thousand angstrom. So that means if you further oxidize it, the intrinsic region is here, and this is a long path. This long path means that you have a very, very large base external resistance that will eventually, that give a large offset voltage, because this VCE offset will also count like RB, RE, IB, IE. So this device just cannot work very well. So we come out the solution is just like doing lateral feeding device. And this is the first demonstration of that this material and this layout can work as the laser. And we put the base metal over here, and which is pretty close to DBR, which is a cavity region. And we only do a very shallow oxidation over here. And so the hole won't transport too long to reach the cavity region. I'll put the emitter metal over here and recombine, and there's a shoot up over here. So here we still see this device is pretty resistive, but as you can see, the previous one we only can crank the base current about 0.3 milliamp, but right now you can put into 4 or 5 milliamp without having too much VCE offset voltage. So, but still, and you can, but it's hard to see from here. But if you just take a point by point, you can see a beta decrease from a 0.5 to a 0.45 around here, and which is an indication of the change of the recombination rate. I mean, that means stimulus emission was enhanced. And so here is the typical data we took from the spectrum. Here, the ratio is around 3 milliamp, as you can show here. Here, 3 milliamp, it gradually become a flat. And you see a 2 mode over here, but because we are not doing a very rigorous oxidation confinement, so it's pretty, the cavity is not that good, but we still show a lasing peak over here. So, okay, so what other interesting part of vertical cavity transistor laser can do is that because it's a transistor, so we have a high impedance, and we can do some funny stuff because first of all, you can see a band structure. We'll talk about some mechanism. When electron coming in and recombine, and as I say, some of the electron which cannot recombine will just swap to collector. But you remember this BC junction is reverse bias. So it looks like a photo detector part. So what I mean is when you generate some photons, and those photons can be reabsorbed by BC junction. And so you create more electron hole pair, and there's a tunneling because it's reverse bias. So the bandgap will shrink, and you can just do a photoresistor tunneling coming in, and those holes can be recycled into a base region. So that means when this is the typical device. Another device we made is another device, but the ratio is 3.5 milliamp. But the typical thing is I want to show you here. So you have high impedance, and you can do like voltage modulation. You just simply sweep this VCE, and you can sweep the line output. You see, you just put more VCE, decrease the line coming. So this is another situation we take because you just to verify like the different VCE, VCE equals to 1, 3, and 6 volt. You have very different line output. And here in VCE equals to 1, actually it was a saturated region. And this in saturated region, you have to understand saturated region is VC is forward diode. And so, but in our case, the device in VC is homo junction. So that means there's no any confinement. So hole will inject into a collector, so it becomes inefficient. But when you operate the 3 volt, which is for active mode, you got less peak. But you switch to 6 volt, your line intensity decrease. So it means that you can just do a voltage modulation. But think about diodes, you cannot do that because it has very low impedance. So give a small conclusions like this is just supposed to demonstrate of the CTO. There's a minus around 18, just because our cavity design is a little bit off from your actual emission, so we have to pull down. And it's a low current ratio of 3 milliamp, which is the smallest current ratio among the transitor laser scheme. And we also demonstrate the voltage modulation capability. So future work, of course, we have to lower extrinsic resistance. We design the cavity, and we have tried to do oxidation to fully confine our cavity. That's it. So, any questions?
Now open for questions and discussion. Any questions? I guess I have a question. So, I guess it's 2 questions. One, are all your growths of all these different lighting layers done here in MNTL, or do you guys get those samples substrates made somewhere else? Are you really doing it in the LSCD furnaces in that?
Actually, we design the material and go in everywhere.
Okay. Okay. And then the second question is, can you remark exactly what sort of oxidation procedure you're going to do to get this current confinement you talk about in your future work?
I think when I read it, I can tell you.
Okay. All right.
Because it depends on the layout. We right now we have a couple of solutions, but we have to make it first.
Sure.
Yeah.
Sure.
Sorry.
Well, that's fine. Any other questions? Y'all are spelling pizza. So. Okay. So if not, I guess Mong-Kai Wu will be outside, so will Jaewon. You can ask them questions outside. We can have pizza. So let's thank them both again.